Lab 3, where we're doing some stuff with permanent dipole magnets. Okay, so what I'm going to talk about is the purpose, the essential concepts, the procedures for both parts, what I found, and the codes and calculations. All right, so the purpose was to calculate the magnetic field of a permanent magnetic dipole and then create a computational model and also code it in GlowScript for both on-axis and off-axis. All right, so essential concepts, we have the B is equal to KRN, where the N will be the slope of our line that we get from the spreadsheet. And then a few more equations. The LNB equation is the actual thing that gave us the line in the spreadsheet. And then the final equation is the Boissarot. Ooh, said that wrong, but you know what I'm talking about. And that gives the magnetic field at any position near a dipole where mu is the field and r is the observation vector. So the results was the magnetic field proportional to distance was negative 2.5277. The magnetic dipole moment was 6.092 amps per meter squared, or amps meter squared, not per. And then the experimental B was found using calculations, and the computational B was made with the GlowScript model. And yeah. So first, the procedure for the on-axis is you get the magnetometer app, and the first thing to do is to find the magnetic chip within your phone and to account for the magnetic field that surrounds Earth so that you get accurate readings. Then to actually get the data, you slide the phone perpendicularly away from your magnet until the field is equal to 20, and then you repeat that for field values of 70, 120, 170, and 220. And then using the data, we calculated the dipole moment. And with this, we used the first equation that I showed, and I ended up getting 6.02 amps meter squared. And then for the off-axis, we find the distance perpendicular that is equal to Earth's magnetic field. Then we move the same distance along the other axis and record the XYZ value and do it multiple times just for scientific purposes. So this was the data. As you can see, the slope of our line was pretty close to the expected value of -3. And yeah, it's all the data. So some observations was the phone was tilted a little bit more than I would have expected for the Earth's magnetic field. Didn't really think it was that strong, but I guess that's why compasses work. And as you would expect in the Boissarot equation, as you brought it very far away from the magnet, it approached 0. So assumptions were that there were no external fields, or that we had accounted for all external fields, and that the magnetometer app is accurate. So now it's time for the coding. So first we set the fields and our calculated mu values and distances. And then we actually found the values and created arrows for both on and off axis calculations. And then finally, we display the answers. And these are my results. As you can see, the yellow arrows are the off axis, and the other arrows, or the yellow arrows are on axis and the other ones are off axis, my bad. And then some sources of error is we could have improperly located the chip. And then there were many sources of electricity within the room that could have skewed the data. So what if we had not accounted for Earth's magnetic north? It would offsite the measurement slightly because we would be finding the resultant of the two fields rather than just the field we're looking for. And then if we repeated the experiment with two of the same magnets stuck together, due to superposition, the field would be approximately double, not exact because there is a slightly different observation vector, but it would be the same direction, especially for on-axis calculations. So thank you so much for watching my video, and please treat me well.